Good afternoon or good morning, depending on where you're joining us from today. This is Mike Mazzarese. I'm a senior engineer at AST Environmental, and I'm joined today by Dwayne Guilfoyle, who's president of AST. He's going to join us on the back end of today's presentation. And so this is about a 40-minute presentation. So we're going to try and get through this all in about 30 minutes and leave about 10 minutes for questions and answers at the end. So the title of today's talk is Quantitative High Res Site Characterization, or qHRSC. And this concept of bridging the gap, we'll be covering this over the course of the next 30 minutes or so. So thank you very much for joining us today. There we go. You guys are all pros at this point. Answer or ask your questions at the taskbar there on the right, and we'll go ahead and circle back with as many as we can answer. If you have to jump off, or if you'd like to share this with a colleague, this will be we are recording this, and it'll be available at our website in the next week or so. And if you're available in early June, we're going to be focusing on a pipeline site in Michigan, where the BOSS 200 technology was applied to treat L-nabble in a large benzene plume. So if you're interested in signing up for that, look for an email from me, or just shoot me an email after we wrap up here. So just a quick explanation of the different components of what we call the RPI group. So, because we'll be kind of referring to the different pieces, the different legs of the stool, if you will, throughout the presentation. So RPI, the founders of the group, the developers of the trap and treat technologies. They also, which we're not going to cover today, but the project support laboratory will be referenced here as we get into the presentation. AST, my company, so we're the national, international project assessment and designers for the trap and treat technologies, and also provide a QA/QC function for the group. And there's our website. And then lastly, there's our partner companies that are spread out throughout the US and internationally as well. Here's the RPI Group Footprint. So here's where we've worked over the years within the US, Canada, Scandinavia. There's some other locations down there at the bottom. And okay, so what is qHRSC? So I promise this is the only slide that I'm going to read verbatim, but there's a lot of important information here. So qHRSC, this quantitative high-res site characterization, is it's a remedial design focused site characterization program that bridges data gaps created by historical site characterization, sampling practices, and high-res site characterization tools like the MIP, MIP, UVOST to provide a 3D quantitative data model that can be used to make project decisions, set client expectations, and develop remedial approaches. And so that's a mouthful. There's a lot to unpack there, and so that's what we're going to try and do over the next 30 minutes. All right. So first off, why are we rolling this out? And so as remedial design, in-situ remedial designers, we've noticed a few things over the years, and we think this program can help bridge that gap between the data, the data that we're given, and the data that we need to be able to develop surgical strategies for our clients. So number one, a lot of the information that we get is old or limited or both. You'll hear me say this in a little bit, but the data is perishable. Soil data soil samples that were analyzed 20 years ago don't help us today. But that's the information that we get, because that's a lot of times that's what is available. Also, sites can have limited geologic or hydrogeologic information. Number of our sites that we work on, the current client for that site, or the current consultant that we're working for, may not have advanced the soil boring out on that project. They're going off of old logs, right? Next, we see HRSC tools being integrated into CSM development programs with really not an insufficient amount of quantitative sampling on the back end. And so, HRSC tools are great. I've used them for probably 15 years, and they help define the box. All right, they help define the extent of the box. How deep is it? How large is it? But they don't help quantify the mass. Okay, and we'll get into that here in a little bit. And then lastly, we're going to tie this all up by using 3D imaging to be able to really pull the site together, pull all this information together, but most importantly, be able to provide that to our clients and stakeholders to help get a nice, concise snapshot of what's going on, what the conceptual site model looks like. So here are the various components that we're going to be breaking down. So the first thing we're going to do, obviously, is look at what's the existing data set look like, and how are we going to fill those data gaps? What tools are we going to use? And that's really where the RDC, or the Remedial Design Characterization process, comes in. If you've been on other presentations with us, that acronym you've heard a million times, and we're kind of expanding that a little bit. So traditionally, it's been just that high density soil and groundwater sampling, as well as the lithological logging. But here we're going to integrate the high-res tools if they make sense, as well as microbiological evaluations, again, if that is what a proposed remedy down the road may contain a microbiological component. Maybe we're doing some upfront analytical work from the microbiological standpoint. And then we're going to take all that information, we're going to tie it up in a 3D quantitative model. And I guess that's really what is different here is we've all seen qualitative models from, let's just say, a MIP survey. And again, that helps us define the box, but from a remedial design standpoint, I need to know the mass. And that's where the RDC process, tying in that high density sampling, really helps answer that question for us, answer those questions. And then lastly, if you can use that 3D model to easily segue into developing a remedial design approaches. So maybe you're integrating excavation, maybe you're using this data to slot some multi-phase extraction wells, or maybe you're using it for injection purposes. All right, so we're going to go through these one by one. So first off, just the data gap assessment. We're looking at the existing soil and groundwater data, geologic, hydrogeologic information, and then figuring out where the data gaps are, right? I've already said, data is perishable, especially on, say, UST sites where we've got, 20, 25 years of data maybe for the site, but maybe the soil is old, or what we have that's relatively recent is just limited. So we're going to identify the data gaps, use the RDC, so use high density soil and groundwater sampling combined with high res where it makes sense, to be able to cost effectively update that CSM. And so this image that you see on the right is from a site that we're working on currently in the Southeast US, and each of the little nodes that you see is where a soil sample was collected. So the RDC process is, again, if you've probably seen this slide from us before. If you've attended other presentations, it's high density, and I mean aerially as well as vertically, sampling of soil and groundwater to quantify and speciate contaminant mass. So this is really important. Again, the information that is required from state to state differs. So if you're on a UST site, for example, you may not be required to report gasoline range organics or diesel range organics. Maybe you're just reporting, say, BTEX compounds, maybe naphthalene. But from a remedial design standpoint, that GRO, DRO are very critical, right? You have to understand the total mass as well as the individual species. And so we do that by dense, and by dense, talking about every 1 to 2 feet vertically, as well as groundwater sampling where it makes sense. So a lot of times, say we're sampling from 10 to 20 feet, we're grabbing samples every 1 to 2 feet. We'll convert that into a temporary well and grab a groundwater sample as well while we're out there. And this information really helps set expectations. Every technology has got limits, right? And so it helps us set expectations with respect to time and budget and realistic remediation endpoints, okay? Do you have to plan for multiple applications? Do I need to bring combined remedies into play? Do I need to excavate, as well as, say, plan an injection? And this information, we get this information cost effectively because that soil and groundwater can be run at the RPI Project Support Lab, which is in Golden, Colorado, and it's run pro bono for our projects. And there is no there's no hook. You don't get a bill from us if you don't end up, say, using a trap and treat technology. This is just the information that we feel we need to understand your site and be able to provide a solid design that's got realistic expectations. All right, so here's just a quick rundown of the equipment that is housed at our project support laboratory. Our office space is actually very small. Most of the square footage in our building in Golden is actually lab space. And so here's the various equipment that we have there. We also this is where we do all of our R&D as well. Okay. So I've mentioned HRSC tools, and how do they integrate into this program? So I guess first, where they're going to be appropriate, they help us again define the box. So especially on these sites where maybe it's defined on 3 sides, but you're not sure where it's going. Maybe you've got a utility that maybe you suspect is being a transport pathway. It's a great way to very cost and time efficiently, be able to survey that area and then follow it up with some dense soil and groundwater sampling again, so we can quantify the mass. But a couple words of, I guess, caution. One is, what this information tells you and what it does not. These are qualitative. Semi-quantitative is kind of a nebulous term, but it's, what you're getting are electrical responses, right? So you're getting this information in microvolts. You're getting a 10 to the 5th, 10 to the 6th, 10 to the 7th, say, microvolts on the PID. Well, that doesn't tell you how much benzene there is, obviously, or doesn't even discern between phase. So how much is in soil, how much is in groundwater? These are really key pieces of information whenever we're planning a remedial strategy. But again, it will quickly tell you, where that mass is, but doesn't tell you how much. And the other thing that I guess I would caution folks on is using confirmation samples to correlate. Personally, I think this is bad practice. I think confirmation sampling is important. But what I mean by confirmation sampling is, okay, at 14 feet BGS, I got a 10 to the 6th hit on the PID. Well, I'm going to confirm that by advancing a soil boring. Okay, at that depth, I got 2,000 ppm of GRO in soil. So you're able to confirm that what you're seeing on the MIP is reality in the subsurface. But what you don't want to do is take that information and say, okay, now this 10 to the 6th on the PID, which is 2,000 ppm of GRO, now I'm going to take that and I'm going to apply it to the next point, or I'm going to try and extrapolate what a 10 to the 5th means. And I pulled a quote off the ITRC website in their high res section, and so I'll just read that for you. Lithology, saturation, and presence of multiple compounds and other factors make direct correlation of MIP response to compound concentrations problematic. And so again, we're using these tools to help define the area, the volume, right, that we need to that we need to further investigate. And so we're going to tie an RDC, a dense sampling program, on the back end of these. high-res surveys. And then we're going to tie it all together in a 3D quantitative model, and I'll give you some more information on the model that we are using here in a minute. But we're taking all that qualitative, quantitative data, lithological information. We're going to tie that all together in a 3D model, and that really is what, when I mentioned bridging the gap, that's really what it gets down to, is we're bridging the gap between qualitative models, limited data sets, and ultimately getting to remedial design. So the 3D program that we used was developed by our European partner, our RPI Group partner based in Denmark, Elskov. And so this is a program that is proprietary to RPI Group companies, and it integrates those qualitative and quantitative data sets very well. And you could actually plan an injection, which I'll actually show you that here in a second. So if you are using injection as remedial approach, you can actually integrate that into this model very easily. And it can also be updated in real time from the field, and I'll show you that. I'll show you an example of that here in a minute. So here's that same site that I mentioned that was in the US, and I'll just kind of toggle back and forth. So here's our cross section, or two cross sections, and we're going to overlay our ultimate injection plan. And the cool thing is that you can actually assign each of these little discs that you see can be assigned different loadings. And as that information comes back from the field, so let's just say that, you know, your injection point 3, you got refusal at, you know, some shallower depth than what you anticipated, that can go in here. Or if, say, you didn't inject as much material as you planned, that can go into here as well. So when you're doing diagnostics as to, all right, maybe I need to go out and offset some borings, you know, it's a lot harder to do that in real time whenever you're in the field. But if this is dumped into the 3D model, it's easy for the project managers to be able to make those decisions. All right, so here's a video of that same site. So again, this is using that same. This is generated from the high density soil samples that were collected. I showed you that map earlier on in the presentation. And here's another site. So Dwayne's actually going to cover this as a case study here in a few minutes. So this site's in Ann Arbor, Michigan, but here's where that model is also used. So what we're going to do, whenever I click the video, you're going to see it go. Hopefully you can see my cursor here. We're going down in depth, and this is soil, PCE in soil. Okay, and then lastly, we're using this model to be able to, you know, develop remedial, to be able to apply our remedial design to the model. Okay, and again, as I mentioned, it can be updated in real time. And so here's another video from another project. This is a project in Europe, but whenever I click the button here, you'll see now these injection points. This is how they were being completed in the field. And so this information can come in live and get updated, and so all of the project managers, stakeholders can actually see, especially when you're talking about any sort of large injection program. Super helpful to be able to see what's going on, look at progress, but again, look at issues with respect to, you know, refusal or any sort of surfacing that we're seeing where maybe we're not getting the total injection volume in. Okay. So we'll go through a couple examples here. I'm going to go through that site that I mentioned already. That's in the southeast here quickly, and then Dwayne will spend a little bit more time on that Ann Arbor project. So this is a UST site, small UST site in the southeast US, and this is the one that I've been showing you a couple images for already. And so it's a former service station for about 50 years, significant petroleum, vadose and groundwater. There's also some NAPL present. Groundwater is about 35 feet BGS, and there actually were some drinking water wells deeper than 80 feet that were impacted in the area. 2 rounds of RDC were completed in 2018 and 2019. Total of 13 borings were advanced using first a 7822 and then secondly a 3230. There was also a deep boring completed with Sonic, and so a total of 11 temp wells were installed, as well as 3 new monitoring wells. And there was a deep well that was screened at that partially weathered bedrock interface to see how much mass was at that interface. So the lithology is saprolite to about 40 feet, partially weathered rock for the next 20, and then competent bedrock deeper than 60 feet. And as I mentioned, there were significant vadose and saturated soil impacts. And so this is all that data that was generated from those 2 RDC events. And there are cross sections. It's also that flyover that I showed you before. And here's the 3D injection. So this is the full scale design for this particular site. The pilot test was actually completed last week, so it's a smaller than what I'm showing here. So Dwayne, I'll go ahead and advance the slides for you. If you want to unmute yourself, you can go ahead and cover the Ann Arbor site for us.
Can you hear me, Mike?
Yes, sir.
All right, great. Well, first I want to say thank you to Mark Quimby and Agnes Taylor with SME, who we collaborated on this project over the last 3 years for a Brownfields site in Ann Arbor, Michigan. And I'll get into the details on this and spend a little more time because the project was rather large and extensive. But to give you a little background, the figure you're looking at there to the left is basically a city block. It's been developed since the late 1800s. There were 2 former dry cleaners, car wash, junkyard, other, I guess, operations that could affect environmental issues, but it turned out that, the dry cleaners were the culprit for the chlorinated solvents that were in the groundwater, which we'll talk about in a minute. There were various environmental investigations that were completed on the site before we got involved in 2018. Those investigations identified, like I said, significant chlorinated solvent contaminated mass in the soil and groundwater. So, there were former remediation and development operations that were completed, but they failed, which basically stalled the overall development of the property for a significant period of time. So go ahead, Mike. So this gives you kind of an idea of the plume of contamination. The source area is pointed over there where you see the PC on the left with the max concentrations in the soil that had been, I guess, defined during historical operations. There was 400 part per million in the soil, 160 part per million in groundwater. The migration was to the east, where you see the one PCE pointing there at 15 part per million in groundwater, and that was at the overall property line. So when we got involved in the project, we were asked to look at designing a PRB using BOSS 100 material to stop the contamination from migrating off-site. And because there was a future development that was fast-tracked, they were going to cover up the whole area. So they were going to limit access to any future environmental operations that could go on there. So the previous investigations, looking at the data, like Mike said, and looking at data gaps, there was the soil profile at the site. There were varied from sands, silts, and clays that were commingled all together. No significant kind of pattern. Groundwater was shallow from 6 to 13 feet below ground surface, extended to 40 feet to a confining unit. Groundwater flow was to the east, and then you had impacts as deep as 35 feet deep in the source area to the west and 16 feet to the east where the PRB was to be located. And I'd already identified where the source area and offsite migration. Go ahead, Mike. So looking at the data gaps from all of that information, the variable soils cause significant problems. Being able to try to model the site, the hydrogeology, the aquifer characteristics, there was a lot of conflicting hydraulic conductivities when we were looking at the information. It made it very difficult to try to look at just modeling the contamination to be able to determine the amount of mass that the PRB would see over a period of time. There were also, like I said, limitations with future remediation based upon the development that was being fast-tracked, that limited footprints of where we could actually implement the PRB. You see that their arrow pointing to a 20 foot wide width that we were given access to do to be able to install the PRB. So that limited what we could actually install in the formation for long term to be able to control the mass that we would have to handle as far as mass flux. So go ahead, Mike. So when looking at our options, existing data versus filling the data gaps, we had two options from a designer, is that we could rely on the existing data that we had and do the best that we could to model the overall mass flux that the PRB would see over a 30-year window. But there was high uncertainty as to what the success would be and really how much mass that well would see, because the uncertainties of the hydraulic conductivity. Nobody could, three consultants over a 10-year period of time could not get a handle on. So option two was to move forward with what we just talked about, a qHRSC program, which would basically increase our confidence level in the overall remedy selection, because we would know how much total mass was in the formation and how much mass the PRB would see over time, and really how that mass is distributed throughout the formation, so that when we're looking at different remedial options for the overall PRB design itself, it would give us a better handle on how to overall attack it. Go ahead, Mike. So it was decided to move forward with option two because of the ability to have more confidence, because this was kind of a one-shot deal. Once the buildings were built, then there was no chance to go in and attack some of these source areas, and really we were stuck with what we could do at that 20-foot wide section along the property line itself. So it really fit the time frame, it fit the constraints related to the construction, and we've had a very predictable outcome based upon moving forward with this qHRSC program. Go ahead, Mike. So they decided, the client and the consultant SME decided to move forward with the qHRSC program, which the first step involved the remedial design characterization. And at this site, the targeted area of the investigation was approximately around 75,000 square feet. So we advanced 79 soil borings to 40-foot depth on approximately about a 30-foot grid pattern. We logged the soils and we collected samples every 2 vertical feet. At every other soil boring location, we offset and put a cluster well in, and in some other areas along the periphery of that 75,000 square foot area, we put 46 nested groundwater wells. You can see a picture of the three screens. They were 5-foot screens that we were trying to get distinct, groundwater zones across that vertical profile from around, 10 feet to a 25-foot depth. We sent off 1,120 soil samples that were analyzed using 8260B analysis to determine the CVOCs, speciation of the CVOCs, and the 185 groundwater samples that also we analyzed for CVOCs, dissolved gases, and anions. We also did our own hydraulic conductivity through some permanent monitoring wells within the PRB itself to just get a better handle of what we saw from a hydraulic conductivity at different vertical intervals, just like that with the well clusters that we did out in the actual plume itself. We use 2-inch wells though to be able to do that hydraulic conductivity calculations and slug testing. Go ahead, Mike. So to give you just the array, real quick picture of what that soil samples to the left there in that figure, and then those are your groundwater clusters that I'd indicated spread out across the whole plume area that you had seen earlier from the historical investigations that had done out there. Go ahead, Mike. So from all of that work, what we found was approximately 4,125 pounds of PCE present within this 60-foot wide swath that started from the dry well adjacent to the dry cleaner that traveled to the location of where the planned PRB was on the eastern portion property line. So what you're looking at there to the right are some heat maps and some cross sections of the soil contamination that was modeled. And then the groundwater concentrations are below that, where you can definitely see at the bottom cross section the actual source area and where the dry well was, and the contaminant mass leaving that. You know, we historically, the highest concentrations that they had found were around 500 part per million. Or 400 part per million in the soil. We found as much as 4,000 part per million in the source area. We think we pretty much found where the old dry well was. The groundwater concentrations were on par with the previous investigations, around 137 part per million in the source area, and then, you know, in the double-digit ppm range across the plume. But we were able to get a better imagery of where that contaminant mass was. So when it came to the actual, you know, injection itself, that we could really target where we were trying to get the most bang for the buck. And I'll get into the overall design in a minute. There was only really parent product. 99% of the mass was PCE, very little natural degradation going on. You know, groundwater was oxic. And go ahead, Mike. So because of the ability to determine where the mass was and how much mass was present, then as practitioners, now we can break the site down. So what it told us is that we could not go over here in this 20-foot swath at where we're identifying PRB2 and install enough material to be able to manage that 4,000 pounds of contaminant mass that was going to hit that PRB over a period of time. So what it told us that we needed to do was to go into the source area and basically try to cut the head of the snake off to eliminate as much mass as we could to reduce the flux that would eventually hit that PRB at PRB2. We also went into, because of the building construction that was going to happen between PRB1 and PRB2, we went on the upside of the footprint of the building that was already in process of being built and installed basically a PRB1 that would also cut off any of that contaminant mass that would be leaving the source area as we were reducing the concentrations in the soil and groundwater within the source, to be able to stop that mass before. We knew that we were never going to be able to access the mass that was under the building footprint, but we knew that we could manage that total mass based on what we were installing in PRB2. So, you know, the takeaway is, because of the ability as practitioners to be able to understand where that mass is and how much mass is there, then it gives us the ability to just look at, you know, combined remedies, even though, you know, this was similar from a CAT 100 to a BOSS 100, you know, technology. It also gives us, just like Mike said, you know, there may be cases where we want to do, you know, source excavation. We may want to choose a different technology, you know, to go over, to go after, you know, vadose zone soils, unsaturated soils that we would not try to treat using the trap and treat technologies. So, you know, that's qHRSC, you know, in a nutshell. You know, the overall goal of what we're trying to do is determine just what we did here, how much mass is in the formation and how that mass is distributed, because then we can, like Mike said, give you all, as the end user, you know, a better prediction of when we're going to get you to the endpoint and be able to optimize the overall remedial dollars that are spent to achieve the overall goal that we're all trying to work to. All right, Mike, go ahead. And that's it. I'd be glad to talk to people. We went forward and did the overall installation in 2019 on that site. It's being monitored over the last 2 years. We've got incredible data. I'd be glad to share it with anybody that wants to reach out to me or reach out to Mike to talk more about that site.
Yeah, I guess that's just to add one thing on to what you said, Dwayne, is that this is one of the sites where we're integrating microbial diagnostics into this site as well. So.
Yeah, in fact, we have baseline microbial data, and then over a 2-year period of time, and it's a nice line of evidence in addition to just VOC reductions.
Excellent. Okay, so we've got about 5 minutes for Q&A here. So we're about 35 minutes in. If you have any questions, once we get off, there goes my email, there goes my mobile. Feel free to reach out after we wrap up, or if you'd like a copy of the presentation, please let me know. And so, Dwayne, I guess, someone's got a question about just small site applicability for this process. And so, and that site that you showed was, one of our largest applications. And so I guess, do you see this being applicable for your average, say, corner UST site?
Absolutely. I mean, it's what we do every day. It doesn't matter whether it's a one well site or a site the size of the Ann Arbor site. That in order for us to be able to determine a methodology and approach as a remediation practitioner, we have to know how much mass is in the formation. And it may turn out that we go out there and we complete, an RDC and we do the soil sampling at the high frequency, and there's not a lot of soil mass present, but we may find that one lens, that's 1 foot thick, that's been keeping that well, above cleanup standards for the last 15 years. And if we can identify where that is and we could target the remediation, then the overall cost of the remediation to finally get that site over the hump, it's money well spent. So, a lot of times on small gas station sites, Mike can tell you that, and we talk to other people about it. I mean, we can do a lot in one day. I mean, a single day of probing out there and collecting, in a day's time, 80 to 100 samples, and that data ultimately will lead to the success of the closure of that site, no matter really what technology you were using. But until you know that, until you know how much mass is there and how it's distributed, the selection of a technology shouldn't occur.
Mm-hmm. Okay, and I guess probably just maybe we'll just go ahead and cover one more. And so it just relates to the high res piece and whether or not sort of where the RDC process can get integrated. So if for example, if someone is planning an HRSC survey, or if it's already been completed, sort of where's our, can we work within the framework if the HRSC has already been completed?
Oh, absolutely. I mean, we can integrate it into the process, or we can do it after the process. I mean, like Mike said, the tools are used to help, it's a simple way to describe, to define the box. And ultimately, what we're trying to do is to quantify the mass that is within that box and how that mass is distributed. So yes, I mean, we often do it. We've done both. We've done it after, and we've also done it to where it's integrated in the field as the HRSC tools are being used.
Excellent. Okay, well, I guess we are 40 minutes in. Thank you everyone for joining us again for this sort of short format presentation. So again, reach out with any questions. Hopefully you can join us next month for our next webinar. Thank you very much. Thank you again. I know we know your time is precious, and we look forward to talking to you soon. Thank you.